What up? All my scientists, my artists, my philosophers, my geneticists, my roboticists, my biologists, my archaeologists, my astronomers. Let's get busy. This has been Busy from the Burbs.
3, 2, 1. Good morning, good afternoon, and good evening, ladies and gentlemen. This is Ben Busy from the Burbs, broadcasting to you from Osaka, Japan. I'm joined by my co-host, John Allen Moore, Trailer Park Master Chef.
What's up?
Today on the program, a very special guest, Michael Nelson, a good friend of mine, PhD candidate in mathematics researcher, mathematician from the U.S., from the United States. Spent some time in England, now back in the U.S., accomplished dancer, believe it or not, but a lot of people don't know. I'd like to welcome Michael Nelson, a.k.a. Six, to the program. Welcome to the program, Mike. How's it going?
Hey, thanks for having me.
Hey,
how you doing, Mike?
Welcome.
Good
anytime.
to have you, man.
So, give the listeners a little background on you as a person, as a mathematician. Give us a little background as to who is Six, who is Michael Nelson, and we can proceed from there.
So I went to undergrad as at Kennesaw State University in Georgia, and I decided to major in math because I was good at it in high school, and I kind of liked it. But somewhere between this sophomore and junior year, I kind of realized I had a passion for it because there's a lot of deep mysteries and connections that you come across when you start studying it, and so it's really beautiful. So I took it seriously, and I ended up doing really well in undergrad, and I ended up getting accepted to Cambridge University. Now I actually went there for a year for my master's, and but yeah, I'm back here now, and I want to get my PhD somewhere, so I'm still trying to go through that application process. So
How was it in college over there?
Oh, it was definitely much more difficult. It was
rigor.
Yeah, very rigorous.
Higher standards, huh?
Yeah, they take it serious over there.
What were you focusing on during your time at Cambridge?
Number theory and geometry.
Number theory and geometry.
Yeah, so studying number theory in terms of algebraic geometry. So have you heard of Fermat's last theorem?
Yes, I have. For our listeners, please refresh our memories.
Oh yeah, it's about an equation.
Just for me.
Oh yeah. So basically,
for those who don't know, Trailer Park Master Chef isn't necessarily the best at math. Neither am I. But I
like math. I appreciate math.
We like the concepts.
I'm not terrible at math.
So do you remember how to graph equations?
Yeah, PEMDAS or rise over run or whatever.
X squared plus y squared is equal to 1. So the set of points x comma y such that x squared plus y squared equal 1. It forms a circle. So there you have a correspondence between geometry and an equation like x squared plus y squared equals 1. And so that gets very deep. And it turns out that you can always associate some kind of geometric object to any equation that I give you. So an equation like x cubed plus y cubed is equal to z cubed. It turns out that there's no integers x, y, and z such that that equation holds, except for the obvious one, x equals 0, y equals 0, z equals 0.
I'm already lost. But no, okay, so you're studying Fermat's last theorem.
Well, not that one in particular, but it's in that area.
So you're saying that like every type of math that there is relates to each other in some way, shape, or form.
Like geometrically? Is that what you're saying? You're saying there's a correspondence between equations and geometry, shapes.
Yeah, exactly. So you have equations and geometry. There's a deep correspondence.
Oh, I think I kind of get what you mean.
So,
cool.
The circle is x squared plus y squared is equal to 1, for example. And you can graph that on a paper and you get a circle. And so
I see.
You can
what about a square?
A square? Well, I mean, I don't think there's an exact equation for it, but the idea is that a square is actually the same thing as a circle in a sense.
I see.
Topologically, they're the same.
I see what you're saying.
So I'm talking about, any shape that you can mold and squished together without cutting a hole in it or something like that.
Mm-hmm.
So
is that what you want to continue on in your PhD studies with?
yeah, I'd like to do that.
Is there like a technological application for that yet, or no?
Yeah, definitely. There's a lot. There's I know in robotics they use algebraic geometry, and I don't know, it gets pretty deep in robotics.
Mhm.
I'm not sure exactly what it is they do, but there's also cryptography. I mean, cryptography is it's number theory all over it,
Yeah.
and like the NSA, they use this thing called elliptic curve cryptography, and you know they're able to hack into a lot of people's or to a lot of companies' computers and stuff because they knew of a certain loophole
Right.
in the algorithm that they gave out. And
Oh, so they can like
Yeah.
solve it.
It
Based
yeah,
reduces.
on
they
the
knew
math
a
that it's-
loophole in the math, right? So they knew they knew something in the math that in terms of the elliptic curve, which actually, by the way, is a donut.
Taurus.
Yeah, it's a torus, right? And so, yeah, so there's an equation for the torus, just like there's an equation for the circle. The torus is also called an elliptic curve, and it turns out that this torus has many really deep properties. and
Right.
it's
Yeah, I've
connected
heard about
to-
this. The
And
Taurus.
the torus is the donut, right?
The torus,
Yeah.
it's a donut
Okay.
shape or like inner tube. I've heard that there's
Yeah.
like a lot of different special properties to toruses or toroidal shapes. Where if it's like, if you're talking about like astronomy or I'm sorry, astrophysics, like the shape of the universe or like all kinds of things. Tokamak reactors, like fusion reactors, are toroidal in shape. There's a lot of special properties to toruses.
Well, just the torus has a property that it's called a group, which is kind of like basically it means you can take any 2 points and you can add them just like you can numbers, right? So I can add 2 plus 3 and I get 5, and you can do the same thing on the torus. It's not obvious, but you can do it, and using that you can get like advanced cryptography going on.
Can I ask you, how did you get started in mathematics? I mean, were you just naturally predisposed to it, or did you have a parent that taught mathematics, or is this a genetic thing? Like, were you kind of like grandfathered in? Was there like a secret initiation process into the?
No, I mean, I wish that did happen so I could have gotten started earlier, but
yeah,
it really kind of started whenever I've always been good at math, but I was never like exceptional, I think. But once I got to undergrad or college, I just started. Decided to major in math, and I started doing it. I liked it, and then I came across a professor who was obviously passionate about it. Right, he was the first guy I met that was really passionate about doing math, and I could see it, and I could see why he was so passionate about it too. I think that's the reason why I kind of got passionate about it too. So it took a mentor or another person who's passionate about it for me to get passionate about it.
Before we get into the main topic of discussion, I do have one last question. If you have something as well, I want to know what right now, besides number theory, besides set theory, what fascinates you about math? I know that we might be. If your answer is infinity, I want us to hold it and go on to the main topic. But what's really fascinating you right now in math?
What's fascinating me right now is that there's a lot of really deep things in math right now that occur in physics too. They occur in the universe, and it's hard. It's really hard to explain, but it has to do with something called the monster group. And these exceptional
monster
things. Yeah, that's a.
Are we talking like supersymmetry? Is this
dramaticism in numbers?
Is this Garrett Lisi stuff? Like
kind of Garrett Lisi stuff. Yeah, because he talks about the E8 group,
right,
which is related to the monster group. He talks about the E8 thing, and he tries to relate it to physics.
For those who don't know, can you explain, like, is this supersymmetry? Like, what is this concept that we're talking about?
Okay, so I'm not talking about any particular concept. I'm just saying what I'm really talking about is how certain structures in math are being used in physics right now too,
I see.
and they're both. I don't really understand it, to be honest, but
It's kind of
I'd like to know
interesting.
more about it.
It's like the code of the universe. I'd like to talk
Yeah,
more about like
you could really say that. I mean, it's a lot of crazy stuff.
yeah, I'd like to talk more about like computational physics and stuff. But Alan, do you have anything more
Yeah, I have
for?
a good one.
Yeah.
I have an easy one. So do you like all types of math, or do you have like a specific just area of math that you either A, don't excel in, which I doubt you don't, or B, you just like it's tedious to do and you just don't even like to mess with it?
Yeah. What are you bad at in math?
What do you not like? Yeah, like
I usually don't like applied math, I guess, but applied math is cool too.
Like, what are those equations called? Like thermodynamical. What are the equations that represent thermodynamical systems called?
I'm not sure. That would probably. I don't know thermodynamical systems.
Like where you do like QED at the end of it. It's not a
that
quadratic.
that's usually you do that after a proof. That's a Latin phrase, and it means basically you're done with your proof when you say QED. So you write a proof and then you write QED.
What are the types of equations that are used in like thermodynamics and stuff? Like what is that I don't know. It's like you have algebra, you have geometry, you have trigonometry, you have
differential equations.
Differential equations, yeah, those.
Those are used in physics in general.
Okay.
So,
do you make much use of those?
Oh yeah,
Yeah.
those are used all the time.
Those are like standard.
Yeah, they're anytime you want to do any physics, that's all you're doing is differential equations. If you have a state, basically if you have a system that's in a state right now, and you want to determine what the state is going to be in say 5 seconds from now, and you use a differential equation to figure that out. That's what it's all about.
You said you didn't like to do much applied stuff, meaning that your strength is in like in pure math, what's called pure math, right?
Well, I wouldn't say that. I would just say that I find pure math more interesting than applied math. But I find applied math interesting too. It's not to say I don't find it interesting.
Is that because you like to be more theoretical and like explore like math more than you actually like to use it for like practical application, or
I just find I find the theoretical stuff more beautiful, and so
it's probably less fun to like measure a bench than it is to like try to figure out how big the universe is.
Exactly. I mean, it comes down to dealing with trying to approximate things to and rather than, let's say, if you're trying to approximate pi, right? What sounds more beautiful to you? Me giving you a list of numbers, 3.14159, like a big approximation, or me telling you that pi is the ratio of for every circle, the circumference divided by the diameter. I mean, what's
the latter? Obviously, definitely.
Right. So
more elegant.
Right. That's what it's all about.
Is there anything that terrifies you about math? Because I could get into like a childhood memory that I have where I was just encountering structures or forms in a dream state that were exponentially increasing, and it was the pace was accelerating so rapidly that it was like actually quite frightening for me, my child mind at the time. Is there anything comparable like that where like you are just so daunted by it, you're so awestruck that it really inspires a terrible fear in you, like, or has it always been kind of like a nice kind of like I don't know, full of wonderment and imagination?
Well, math is never easy. It's always every step of the way, when you look forward to see what you have to deal with next, it always looks like a nightmare. It's like, how are you going to understand that? What is that?
It makes me feel better that you also feel that way about math.
Right. Yeah. It is for everybody. Even for the experts. When they'll look at something and it'll be profoundly confusing or intimidating, and they, they'll feel like they'll never figure it out. But what the joy that you get is once you do understand something, you can kind of you look back at it and be like, wow, it wasn't that difficult. Now that you understand it, it's actually easier.
How would you characterize the phenomena whereby you go from one state of not knowing through that point of bifurcation to another solid state of knowing? Is it Boolean, like a switch just flips, or is it more gradiential or more gradual?
Sometimes it's both. Sometimes sometimes it is a switch. Sometimes like, aha, that I get it, or sometimes it
just clicks.
Yeah, it takes a long time, and it takes time. After gradually you kind of get used to it. You get used to the concept, and then eventually it becomes ingrained in your mind, and it just becomes that's obvious to me now that I've really put a lot of focus on it.
Do you walk around and like dream of math? You must see math in everything.
I've had dreams of math before whenever I studied really hard, like one night, and they're usually not comprehensible or anything. They're just they'd be like the thing that John mentioned earlier about the scary nightmare dream or something. But,
yeah, that was me.
Oh, sorry, Ben.
But you could also like graph the curves of like a beautiful woman, right? Isn't there like a rise over run for that? Or
yeah, probably.
Yeah.
Yeah.
You could figure it out one day.
Yeah.
Isn't there's something to this, like people talk about symmetry being like really attractive. Like if someone's face is very symmetrical or whatever, like they're somehow more attractive. Like
so yeah, that's another thing. Symmetry is also very beautiful. So symmetry turns out in physics, every symmetry in the universe corresponds to a conservation law. So, for example, one symmetry of the universe is that the laws of physics are the same as they are now as they will be in, say, 5 years from now, or 5 years ago, or any time at any time from now or whatever.
They're the same, but can you qualify that? Because isn't the universe is expanding or it's contracting or whatever, respiratory
universe. Well, that doesn't matter. The point is that the laws of physics, like the gravity, gravity has a certain equation to it, and you can solve the equation to figure it out. And that equation is the same basically throughout time. That's a symmetry of gravity. That corresponds to conservation of energy. So what that means is conservation of energy is true if and only if this symmetry is true.
So basically, beautiful people are good conservers of energy.
Yeah.
Okay.
And I think we can tell by Los Angeles that that's not true.
Yeah, that's right. In South Korea
the least
as well,
true
where
thing.
85% of people get plastic surgery. So now he can instantiate good conservation.
That is insane, though.
It's quite interesting. What about, so wait a minute. Okay, so the laws of the universe, mathematics.
So is that how is that how most things are proven then, huh? Because you basically know that one thing is true.
Yeah,
and then you find out that through some connection that this is also connected to this, and this can only be true if this is true.
That's right. Yeah. So if we, for example, we found out that conservation of energy, so for some reason was not true, the energy wasn't conserved, then all of a sudden you could say that the laws of physics for any kind of system like gravity has changed. It's not the same. Right? So maybe gravity was weaker at one point in time. That's what you could say.
And that can cause like massive shifts in other parts.
So if gravity was stronger, like, say 10 years ago, which we don't think it is, based on experimental evidence. But if gravity was stronger 10 years ago, then that means conservation of energy for gravity or gravitational energy would not be conserved.
I have a question though. Like this might be kind of like whatever, non sequitur or whatever. But I mean, what if the laws of physics had been scaling down after all these years? Would that wouldn't make a difference, would it? Because like the values in the past would be relative to the scale of whatever the values in the physics were at that given time. Like, if does scaling have any effect on this? Like,
Well, yeah. So, like I said, if gravity was stronger in the past,
Mhm.
or if it was weaker in the past, then that means conservation. That means energy is not conserved.
Mm.
That means that the law of conservation of energy is not true.
Mm-hmm.
And so it turns out that every single conservation law that you have, say you have conservation of energy, conservation of momentum,
Conservation of mass.
right? Yeah, all of those, they correspond to some symmetry. Now, conservation of mass is actually part of energy too, according to Einstein.
Right.
So it's actually mass energy. Which you should think of mass. You should think of mass as energy, basically.
Right.
So that's the same thing as energy. But conservation of charge, right? You can't all of a sudden have a electric charge go from Mars to here, out of nowhere. That's conservation of local charge. There's a lot of conservation laws out there, and they all correspond to some kind of symmetry of the universe. The conservation of momentum symmetry corresponds to that symmetry is the one where the laws of physics are the same for me here at this point in space as they are for you in another point in space. So it doesn't matter what point in space you are, the laws of physics are the same there.
Isn't it true that if you drop an apple off the south coast of India, that it falls imperceptibly slower than if you were to drop an apple, say, in New York or Paris or something like that? I heard there was like what's known as a gravitational depression there, or something strange given the shape of the Earth or the electro.
Maybe the bulge of the Earth.
Yeah, it's like the bulge of it or
Well,
something.
yeah, I mean, I guess if there's more mass, concentrated near the equator, I think there'd be a very slightly stronger gravitational force there. So,
But it's not going to change the overall laws of physics.
right,
The
the overall
gravitational force will just be greater.
Yeah, right. So the gravitational force would be, if we had the same Earth that existed throughout all of time, say, for example, gravity would always be the same, right? It'd always be 9.8 or approximately 9.8 meters per second squared.
It's fascinating.
Right.
What about Alan Guth? Like, this is an argument. I want to get to the main topic of discussion. Listeners, if you're listening, and I know that you are, we will be getting to the discussion point at hand. But this is just too interesting to let go. Now, we spent a lot of time, Six, in a room called Debate Faith on Stickam. And there was many debates that would happen there. Okay, AAL was quite boisterous and loud and annoying in his own way, but I mean, he does what he does. It's what he does. Now, there was a guy. He was a statistician. His name was Nichiren's Buddhist or something like that, and he brought this argument up that stated that the laws of the universe, that is to say, the laws of physics that govern the resulting universe, according to Alan Guth, who is, I think, the father of the inflationary model of the universe, it was said that those laws may have existed before the physical universe, and people were optioning this as an argument, kind of de facto, for God. Now, I've heard many mathematicians who espouse a belief in God. How do you resolve a belief in a higher power, a deity, and does that factor in at all for you? And how do you resolve this idea that Guth put forth that perhaps the laws that dictate the universe actually preceded the universe?
Well, I think what Alan Guth is talking about is something different, but you should take most of that stuff as pure speculation, for one, because there's no evidence to suggest any of it. Even even cosmic inflation, there's no evidence to prove that it's actually right.
Like mathematically, you mean?
Well, I don't know about mathematically, but physically, there's no evidence, and that's the important point. I mean, there's a lot of mathematical consistent things that I can put forth. It doesn't mean that it corresponds to something in the universe.
But the background microwave radiation or whatever, isn't that what they use chiefly to prove that inflation is happening?
Yeah, but they said on June 19, 2014, lowered confidence in confirming cosmic inflation findings was reported.
Interesting.
So they don't. There's no evidence to support it. There's actually a lot of theoretical physicists who come out against cosmic inflation. So it's not like it's a settled matter.
This is the problem.
So you can kind of go back to that web journalism thing where you get like half wind of something that someone discovers and it gets blasted all over the internet like it's pure fact, and then people are like misinformed about
totally.
pretty like large scientific like
So let's broach that topic of discussion, because this is what we wanted to talk about at the top of the show. And this is why we brought Six on. Because
discoveries.
Yeah. What do you make of the disservice or the service that science journalists provide both to scientists and the public at large? And what can they do to not be a disservice? Or serve as a disservice.
They can try to stop giving out like overly exaggerated phenomenal headlines that obviously, anything that you find that is surprising or really surprising, you should always take that with a grain of salt.
Right.
And you should wait and try to see if there's a scientific consensus out of it.
Right.
Now, the best way I think to get that is to follow well-known physicists that are very credible. A lot of them have Google Plus pages, like John Baez.
Google Plus, so these guys are typically on Google Plus, not Twitter. That's like their platform.
Or Facebook.
Yeah, I think so. I think the most of them are on Google Plus.
All right, awesome.
But they might be on Twitter too. I don't know. But I know some of them are on Google Plus, and they're very credible guys.
Interesting.
But one of them I recommend is John Baez. But
how do you spell his name for our listeners?
John Baez.
Baez, Baez.
Okay. Yeah. But yeah, so I mean, the problem really is that most really surprising new discoveries in physics turn out to be wrong.
Right.
So it doesn't really matter, if there's going to be a journal that's going to any surprising new discovery that comes out on the archive or whatever, a journal is going to mention it, and it's probably going to be wrong. But the journal that mentions it is probably they don't know any better.
Right.
And because the idea is that it's easier to find something amazing by screwing up than by actually finding something amazing.
This is the principle, right?
Do you think that there's
proceed?
Do you think that there should be more like actual scientific professionals involved in scientific journalism than there are? Because you feel like that a legit professional would like know the bounds of when release
definitely
information like that.
Definitely. If you had you see, it's really hard, like I said, because most new discoveries that come out, right, they usually come out to be wrong, and because it's easier to screw up than actually finding something amazing, and so it's kind of hard. I understand why many journals do mess up on this, because it is actually really hard to get it right. Now, on the other hand, there are some cases where all the physicists are, they're bashing a particular theory or whatever.
Right.
And the journal still comes out with it, and it's over sensationalized or whatever. And that's the case where journals can do better, for sure. Because now, I'm not sure exactly how they would get a consensus out of physicists, but
is there a lot of push and pull within physics or within math, or is there kind of
If they just presented it how it
consensus.
is, like even if there is push and pull, instead of like making it one way or the other, or just trying to make a great headline, like Michael was saying, how about you just have the truth of the matter? Like it could be this, it might be, but there's some guys that think that it might not be.
Right. Well, that's what I'm
and
saying.
they maybe
though,
present both arguments.
Yeah, but oftentimes those like pigeonholed arguments are just fallacious as hell. You know what I mean? Like the reason why they're not representing both sides of the argument is because one side is stupid.
My advice to my advice to the general person in the audience is to not follow journals at all. Is to follow, like I said, credible physicists on Google Plus or Twitter or whatever. That's where you'll get
is a better source.
Yeah, that's where you'll get the best information, because they talk about, for example, John Baez. He has a lot of. He's a well-known blogger. He's actually been blogging since like the 1980s. He talks about. I know he's really. He's a very good
Morse
writer.
code.
He's a very good writer too. So he's wrote. Recently, he wrote this thing about. Let's see here. Corkscrew orbit. Let's see here. Oh, yeah, here we go. He says, can planets have corkscrew orbits? And he said, the magazine New Scientist recently announced an unbelievable discovery. And he said, but when you read something unbelievable, maybe you shouldn't believe it.
Right.
When the planets get close to one another. So basically, he just goes into this article and kind of shows you why it's not true that you can't have a corkscrew orbit like the way that they're saying that you can. And he gives you a picture of kind of like what the corkscrew orbit would look like.
But the corkscrew orbit, like if you have the star passing through space, wouldn't this shape of a corkscrew naturally kind of present itself?
Well, they have two stars here. It's in a two-star system, and they try to make it so it perfectly holds it in the corkscrew orbit. But you can't do it. And he describes for the layman, not for a mathematician or physicist, but for the layman, why it couldn't work this way.
Do you feel like there is an orthodoxy at work in the sciences preventing honest revolutions from taking place, or do you feel like if there were a truly revolutionary idea, which was true, that it would float to the surface, like it would just present itself and emerge as the victor supreme of all mathematical or scientific theories? Or do you feel like there is, I mean, I hate to say the C word, but a conspiracy to kind of dictate the terms of science and what is factual and what's not?
Well, I think any revolutionary idea would take a few years to, before consensus gets behind it. But I think most people who are studying this stuff, most experts in this field, when they see a revolutionary idea, they would know that it's a revolutionary idea, and they would mention it. So, for example, in math right now, there's a guy who, I think his name is Shinichi Machizuki or something, and he's recently come out with this theory trying to prove this thing called ABC conjecture or something. And it's something that apparently nobody really understands. His proof is based on this theory that he developed, but it seems like a lot of people are talking about it like it is a revolutionary piece of work, but it's going to take a while before they understand it.
That's interesting.
So someone could produce an idea that nobody else understands. What if that person has no credibility behind them to present the idea?
Yeah, like
would people
Von
spend
Helton
months like
or
studying
David Icke
Von
or something.
Helton? Let's just say Von Helton, Stickam character from a long time ago. Funny
yeah.
guy. Let's just say Von Helton presented like a 32-page equation that was like proving some
on reptilians.
Reptiles on reptile presidents, and he presented it for review. Like, would that someone actually review that, or would they look at it? Okay, fuck you, idiot, and burn it?
They probably wouldn't take it seriously. No.
That's what I'm afraid. What I'm afraid of. I have this fear. Like, what if Von Helton? What if he's correct? You know what I mean? Like, what if we're all wrong? What if the scientific establishment, mathematical orthodoxy, like, is just incorrect, and Von Helton's crazy reptile theory is actually right. It's a terrifying nightmare that I have.
Then I guess we're all fucked.
No
He's
God.
a Socrates of his time.
No God. So science journalism, how much science journalism is actually good? Like, do you ever read a piece of science journalism where you're like, hey, they got it pretty good. They did a pretty good job. Or is it always like they always fucked it? They always fucked
There's
it.
always something wrong.
There's always something wrong.
At least 90% of the time, there's always something wrong.
God
I'm not
damn.
saying that. I'm not saying that they're that they're completely wrong, but there's always something they get wrong.
Right.
And it's not, and that's not like it's bad on them, because it's really easy to get it wrong. It's not, because the stuff that they're talking about is not easy. It is complicated.
Mm-hmm.
So when they talk about black holes, or they talk about quantum mechanics or whatever, they're going to get something wrong. They're going to get something that's misleading. It's just,
you feel like that they should probably get like the mathematicians involved in the studies that we're talking about more involved in the writing of the articles.
Right.
Well, that's why, if let's say that the article is written by a credible physicist or an expert in the field, then it probably is a good source to read. But the problem is that most of these journals are written by popular magazine editors,
like
who
fans.
Right, they're not theoretical physicists.
And like getting the physicists to take time out of their day to like write the article would be akin to like getting the gods to come down out of Mount Olympus to like, mess with the mortals amongst us. Like they just often probably wouldn't have time in their day. I'm not saying that they think that they're better than people. I'm just saying that like,
Well, yeah, I mean, but they do write stuff. Like
That's
I said,
true.
you can follow them on Google Plus. They write stuff on their own.
Google Plus
So,
is like the place for like scientific professionals to like. They don't use Facebook at all, do they?
Yeah, no, they don't use Facebook.
Outstanding.
But yeah, I mean, there's definitely a lot of.
So a normal day for like a theoretical mathematician, let's just say like, well, I want to map this out because I've always kind of wondered what this looks like. So like if you're a theoretical physicist and you go into work and you have your coffee and you sit down at your desk and with your, I'm assuming your like ink pen and all your crap, just start like solving equations. Yeah, with like a feather on it and stuff, and you gotta dip it in a little ink.
No, you use chalk and a chalkboard. That special Japanese chalk that mathematicians were stockpiling until they stopped
or do
selling
you
it
just
recently.
or do you just stand there with a blackboard and like you just solve equations all day and that's what you do
On a
until
window?
like you figure something out? Yeah, on a window.
No,
with a bar of soap.
mathematics really isn't. It's really about understanding structures, and it's about understanding concepts and stuff like that. So you have to wrap your mind around some of these things.
Is
You
there
have to try to.
Are there many problems that you've encountered which were just intractable, where you couldn't get anywhere, you didn't know right from left, and is there a language to math where like you get to the point like you're a PhD candidate where no matter how difficult it is, you can still kind of get into the cockpit, you know where the throttle is, you know how everything works.
I mean, there's sometimes you do run into walls, and you're not going to go any further.
That's amazing to me.
Yeah, I mean, it's not. There's definitely a lot of, like I said, math is complicated. It is definitely complicated, but at the same time, math is actually the easiest subject. I think it's it's the simplest subject scientific subject out there. And the reason I say that is because when you prove something in math, then you know it's true. There's no everything about it. But if you study something in biology like a cat, that's what is a cat? A cat is made up of hundreds of thousands of molecules that make it up. I mean, it's a very complicated thing when you really get down to it.
Yeah, millions.
Yes, and there's tons of mysteries just about a cat, right?
Right.
So
just living organisms in general, just
right,
like insanely complicated.
Yeah, it's way beyond our comprehension. But at least in math, you can actually sit down and prove something. You can actually understand something very well.
Mm.
So that's why I say it's the simplest in that sense. The only reason that it seems complicated is because it forces you to sit down and improve things, and that's not something that we're used to doing.
Do you feel like math is taught incorrectly in schools?
Oh yeah, definitely. I mean, well, for one, the people that teach it in high school
Mm-hmm.
usually don't know the end. Like they don't understand the bigger picture, and they usually they usually teach kids to memorize this, memorize that, blah blah blah, but they don't teach the underlying background to it. So, for example, algebra is a perfect example. Algebra, they teach you rules to remember to do with these equations, right?
Mm-hmm.
So, like the distributive property, you can take if you have equation x times 1 plus 2 or something, that's the same thing as x plus 2x or something like that.
Right.
Right? They teach you all these rules in algebra, but they don't really teach you, why should you study those rules? And it turns out, like I said, is related to geometry. And it turns out that when you do these properties, you do these rules, it's the same thing as, say, intersecting two lines. It'll come down to that's really what it comes down to. You're doing geometry on paper, basically.
Who's your
and so
yeah.
they're not, if you don't have that in mind, then it's much harder to learn it, because all you
Probably to
you
grasp,
think you just
yeah.
you're just thinking that you're memorizing something,
Right.
and
Because
that's never.
I remember when I was learning, that's 100% what it felt like. You kind of just like throwing numbers at a chalkboard. And now it's funny because I'm way better at math now than I used to be, and I make jokes like I'm terrible at it. I'm not too bad anymore. But before, it was mostly because I just couldn't focus long enough to even like care about it. I would get bored so quickly, and I just couldn't. I just wasn't retaining anything basically.
What do you
And now I've kind of, I don't know though. It was a weird situation. I would always like to try again.
What do you say about the argument where people are like, you should always have to know how to do, for example, long division, because, you might not have a calculator or whatever. What do you think about the merit behind unassisted calculation in schools, primary schools, for tests? Like, now most classes have calculators or allow calculators, but in some testing situations they don't. Like, what do you think about the assisted versus the unassisted? Do you have any perspective there?
Well, I think as long as you understand what you're doing, how it works, then there's nothing wrong with using a calculator. And using a calculator can help you, definitely a lot, because it'll get you through all that computational mess that you don't need to get through if you already understand it. But with that said, it's very important to sit down and go over the computation, do it yourself, so that you understand what you're doing, you understand what's going on. The whole point of a calculator is to skip over all the boring details that you've already done.
Expedite the process.
Right. But you have to make sure that those details you already know how to do.
Who's your favorite mathematician? Besides Sir Isaac Newton. Everybody says Newton, right? Because he invented calculus or whatever. Like, besides him.
I don't know really. I mean, I guess there's a lot of famous mathematicians I could talk about that.
Maybe contemporary. I guess you said John Baez and...
Yeah, John Baez. I like him a lot. Yeah, he's a mathematical physicist. Hey,
this
so you
guy
talked about
Shinichi Machizuki.
Oh, I don't really know much about him.
No.
And his work is beyond my comprehension, to be honest.
Interesting.
It's beyond pretty much most mathematicians' comprehension.
He's like invented. Mathematics seems to be like one of the few disciplines where you could conceivably make a little world for yourself in which you can rule as king. And if you obfuscate enough, like, no one can penetrate, and if they penetrate, then they've already bought into your system, and you have them, like, no matter what.
Yeah, this guy, he's definitely done some new things.
He's shaking things up. I like people that shake things up.
There's a good report. Speaking of shaking things up, there's a report from last year. I think this is one of those crazy headlines people were talking about. But it was basically this guy James Gates. He finds computer code in the string theory equation.
Oh God!
And he like had presented it at one of these big like scientific conferences in front of Neil deGrasse Tyson. There was like a video on it. What is your opinion on that? Did you get to look into any of that type of stuff or no?
I didn't see about that, but that sounds pretty funny.
He was seriously
physics?
like, this dude was like seriously, I found binary code like Windows like fail safes built into the binary code, like built into string theory somehow.
Yeah, like I said, if it sounds crazy and sounds like that, it's probably not true. You always wait for a consensus.
Yeah, but, there hasn't been one yet either. I'm ready for it though. I want to find out if we're really living in the Matrix here.
Yeah.
Now, about string theory is definitely a lot of people say it's more of a mathematical subject than physics, because there's definitely a lot of beautiful math in it.
Mm-hmm.
But the problem with string theory is that there's no experimental evidence to support it yet. So
because you can't.
Well, yeah, I mean,
we have the Large
right?
Hadron Collider,
right?
right?
I don't think it's impossible. It's not falsifiable. So they could always say, if we never find something that helps prove string theory, then they could always say, well, the energy levels are not reached yet. They need to, and it's not. That's why it's not
functioning correctly. Isn't it true that like in physics, like quantum physics specifically, like every theory that they've ever come up with, or not maybe every single one they've ever come up with, but they come up with more provable theories in quantum physics where they'll come up with something that's like theoretical and then years later it turns out to be true. Like,
what's their average?
Is it as accurate? Yeah, like are they batting 1,000 or is it like every couple?
Quantum electrodynamics is said to be the most successful scientific theory to date. And that's because they come up with predictions, like say the the mass of the electron or something.
Right.
They come up with the predictions and they get accurate to like within like a millionth of a decimal place or something.
Yeah.
And so it's
That's
very
highly accurate.
Right. That stuff is like top of the line accurate.
Quantum physics,
they haven't missed yet. That's pretty great.
Like quantum physics, like when it started, like in the 1930s, isn't like all of modern computing and like semiconductor technology is based on quantum physics to some degree?
I don't think so. No? I think that they're trying to come up with the quantum computers right now that's based on quantum physics, but
but I mean like the physics behind semiconductors, like these work by way of like some kind of quantum principles or something, given like the way that electrons propagate through or pass through semiconductive materials.
I've heard that based on some quantum principles that the semiconductor is able to lose heat like more efficiently, but I'm not sure about that. Like, I don't think there's anything definite about that.
What do you think? What do you think about quantum computers and like the work of D-Wave? Do you believe that? Like, can you explain something? We might be kind of getting away from your area of expertise, but quantum annealing. I've heard this term used. I'm not sure what it means, but it's the principle by which a quantum computer can actually quantum compute, right?
Well, quantum computers they're still in their infancy,
right?
But there's definitely I think they carried out quantum computational operations in very small number of quantum bits. The whole point of a quantum computer is it's based on something called a qubit, which is basically it's like a superposition of a classical bit, a false or true, whatever. But basically, think of it as it allows you to do things in parallel. That's probably the best way to explain it.
Yeah,
you can do
that actually this year they made a huge breakthrough in that in October, allegedly. But apparently, qubits made from standard silicon transistors. So they have actually made qubits using silicon transistors as like a logic gate of an on-off switch, kind of how like a 0 or a 1 would be for binary.
Because before you needed all of this really kind of fancy proprietary equipment in order to achieve the qubit or the quantum annealing or whatever.
Now they're just using normal silicon. It looks.
I wonder how many more years it's going to take for us to get like legit no shit quantum computers. I know the D-Wave units at Lockheed bought one, Google bought one. They're supposed to be able to quantum compute, Q compute. But
I don't know.
Do we even know what we would do? What would we even do with that much computing power? I don't even think we have a capacity to use the amount of computing power we have now. I don't think we're on the level to even. I don't know. I mean, I'm not like as versed in it.
What do you think, Six?
Well, I think 10 years from now, or 15 years from now, there will be something that we wouldn't even expect to be a technological breakthrough. And I don't know if it's going to be quantum computing. It will be something else that we're not thinking about right now. Because that's always what happens.
Right.
It's always people predict, something's going to be big in the future. It always comes out to be something else that's big, like the internet.
Flying cars have been on the back burner for a long time.
Right. Nobody predicted the internet, but look at how crazy big the internet is. How much of a technological advancement this thing is.
It must be in every single podcast at this point that I mention this guy, but Nassim Nicholas Taleb is a former quant who made a bunch of money in hedge funds, but he was kind of a black sheep in the industry. He wrote this book called Black Swan, the nature of highly unpredictable events, and he talks about that, how, for example, the internet or whatever, September 11th, these are black swan events that no one can predict, and that when they happen, then what we do as human beings, we retroactively go back and talk about how, oh yeah, we saw that coming the entire time, because they were so transformative that in order for us to maintain our sanity, we
that was gonna happen sometime or another. We
invent this fiction.
Yeah, I would agree with that.
So what's your prospect for the future? Like, what do you see looking towards the future? Do you have any thoughts about that? Whatever, even as general as it's gonna get better, it's gonna get worse, it's gonna.
I'll say this about, at least for physics, they're right now they're trying to find the Higgs boson. So they don't know for sure if they detected it or not. So
yeah, I thought they found it.
Well, I think they did, but they're still like in the process of verifying it.
Mm-hmm.
But
understanding it, even, because you can say you found it, but then
so maybe
you got to figure out, did you really find it?
Right.
Right.
So there's that, and then there's also supersymmetry, which a lot of people are hoping that we're going to find that. Mm-hmm. And there is a consensus in the physical field about that. So
could you foresee in the future, if the Higgs is finally detected, us being able to produce, and here I go with the science journalism, right? This is the problem with science journalists. They can't just accept the discovery alone and be satisfied with that. It's always about, how can we market this? How can we turn this into a product? They kind of operate from that perspective.
Right.
But, I mean, bear with me for a second. So in terms of applications for, if we discover the Higgs particle, we essentially have cracked gravity, right? We've figured out what gives matter its mass, right? And
not quite.
Not quite?
No, because most of the mass that is used in gravity doesn't come from the Higgs boson. It comes from energy in general, which is kind of so the Higgs boson only explains the mass of elementary particles, right?
Right.
So mass in general, just think of as energy, right? So
Right.
any kind of energy produces mass. So most of gravity, that is a large scale kind of a phenomenon. We don't really understand the quantum gravity yet.
Oh,
So we
God.
don't understand gravity at the small level. So maybe it does play a role in quantum gravity, but we don't understand it basically. But at
Would
the
there-
large scale level, it's mostly energy, which comes from, say, electromagnetic energy. All that confined to a certain space makes mass or energy. Mass is just another way of thinking of energy.
What
But
Right. What I'm fascinated in is like, I could be completely disconnected from what you just said because it was amazing. But what I'm saying is like, in engineering, in material science, where there are ways that we can produce materials, for example, that are like high temperature superconductors and stuff like that. Like, if we get to the point where, okay, we discover the Higgs, but you say that most of the gravity that affects like matter.
that affects us. Yeah. So most of the gravity that we're, the Earth, the gravity of the Earth, and all that and stuff.
It's energetic.
Well, mass is energy. So
Right.
So basically, Einstein showed that the only thing that causes gravity, at least on the macro scale, is energy and pressure. Right? So if you have energy and pressure, that causes gravity. So actually, the sun has pressure in the middle, right? It has a lot of pressure inside, and that actually produces extra gravity. Like that, it's not something that most people are aware of, but so the sun has energy, right? And it also has pressure inside. It has a lot of pressure, and that actually produces more gravity. So it's kind of like so pressure also plays a role.
We're like in
I didn't even know that.
We're in
I
like
thought
a
it was
gravitational
100% mass.
field.
Well, yeah, mass. So mass is the same thing as energy,
Right.
and so mass you can think of as energy. So it has a lot of mass. Sun has a lot of mass, but it also has pressure inside, and so pressure is also causes gravity.
So that produces
insane.
like a field, a gravitational field, right?
Right.
Whereby if we were to go to a different planet, Earth-like planet, around a different star, we would definitely be exposed to a different kind of gravity.
Well, it just depends on if it's if it's a different star, it wouldn't be the same gravity. It would be different.
Oh, so that whole Goldilocks zone thing, that really, I mean, I'm sure there's still plenty to pick from, but it's probably a lot harder to find. I mean, I guess our star is pretty average.
Yeah, our star is I think it's pretty average. I mean,
I know it's not like super big or anything. I'm pretty sure it's actually on the small side.
And I'm pretty sure they've already found hundreds of other Earth-like potential Earth-like planets, right? The potential planets in the Goldilocks zone or something like that.
Right.
So it's not like it's super, super rare.
Yeah.
We're getting towards the end of the broadcast, Six. I want to thank you very much for coming on the program. If people are looking for your work, or if they want to check you out or get in contact with you, do you have like anything that you would want to give to people as far as that's concerned?
I don't have anything right now, but I'm
Nothing
sure
to promote right now, but maybe in the future. We would love to have you back on the program in the future if you're up for that.
All right, just let me know.
Awesome. This was
be good, man. That was fun.
Yeah, this was really edifying. Alan, do you have anything else for Six before we say goodnight to everyone?
It was great talking to you, man. Like, I learned a lot. I actually would be more interested in having another conversation just like this one. That was good.
Okay, yeah, definitely.
And I can beat you up some more.
Yeah, this was awesome, Six. Thank you very much. I want to thank everyone for listening. If you were educated or entertained by this podcast, probably more educated, I would hope, than entertained, but hopefully both. Please click the PayPal link and donate to our program. We are 100% user, listener supported. If you are using this information, if you are listening to this podcast in your car, in your headphones, on your iPod, wherever, on your computer, YouTube, at work, while your boss isn't looking or listening, definitely, please click the link. Give us a little dough so we can help keep the lights on here at the Get Busy podcast.
That'd be great.
I want to thank Trailer Park Master Chef. Check him out, Instagram.com/Trailer Park Master Chef, and he will be posting those recipes on the website soon. Look forward to that.
And I'm a little bit behind right now. I got to get on making some more recipes. It's been a little bit since I've been in the kitchen.
It's all good, brother.
But I will be back.
I know we got some requests from people that were wanting to see some of these recipes, so we'll check those out later. And of course, thank you very much to Michael Nelson, aka Six, for coming on the program, brother.
Oh, no problem. Thank you.